Let's look at the procedure for balancing redox reactions. So a redox reaction that's short for oxidation and reduction is one simply which involves the transfer of electrons from one species to another. And in a complete redox reaction, we have two independent half reactions that take place. And these half reactions are known as oxidation and reduction. Let's take a look at how each of those half reactions looks. So in an oxidation half reaction, we can describe oxidation in two ways, both as the loss of electrons or an increase in oxidation state. And an example of this would be copper going to Cu2+. So in this case, copper has given up 2 electrons to become 2 positive, and its oxidation state has gone from essentially 0 to +2. So that's an increase in the oxidation state. We can look at reduction, and an example of a reduction would be Cu2+ going to Cu. And so here we have a gain of electrons, or we can describe this as a decrease in oxidation state. And the common mnemonic device for remembering which is Leo Ger. So lose electrons oxidation, gain electrons reduction. So the half reactions in a redox reaction describe the chemical changes that are occurring at the electrodes. And each of the half reactions that takes place, the oxidation and the reduction, contributes to the potential difference and therefore to the cell potential. So it's important that we keep track of what's happening with the electrons. So whether a species is giving up electrons or gaining electrons, that helps us to understand how the electrochemical cell will behave. So we can now start and look at the process for balancing a redox reaction. And there are just a few notes before we go into the steps. The first note is just a reminder that an aqueous solution means ions in water. And we are going to find that there are many steps to this process. So this is a multi-step process. And there's one process that we use depending on if the solution is acidic or if the solution is basic. If it's acidic, then we have H+ ions remaining in the solution. If it's basic, we have OH- ions remaining in the solution. And the procedures are pretty close. Basic just has one more step than acidic. So let's take a look at these steps and work out an example along the way. Let's consider as our example reaction Fe2 plus in an aqueous solution and MnO4 minus in an aqueous solution going to Fe3 plus in an aqueous solution plus Mn2 plus in an aqueous solution. So this is the reaction that we are going to attempt to balance. The first step is that we need to identify the oxidation state of each atom so that we can then identify which atoms are being oxidized and which are being reduced. So the first step is to assign oxidation states. And this is something from chemistry. So in the example here that we have, just sort of going along from left to right, I have Fe2 plus, I have Mn7 plus, I have O2 minus, and then on the other side of the equation I have Fe3 plus and I have Mn2 plus. So the one that's being reduced is manganese because it's going from 7 plus to 2 plus, and the one that's being oxidized is iron because it's going from 2 plus to 3 plus. The second step in this process is to separate the overall reaction into two half reactions. And those would be for oxidation and reduction. So in our example, the oxidation half reaction is Fe2 plus going to Fe3 plus, and the reduction half reaction is MnO4 minus going to Mn2 plus. Now the next step is that we need to balance this reaction in terms of mass of the different species. And we're going to do that to each half reaction separately. And we're going to do this in a three-step process. The first is that we're going to balance all elements other than hydrogen and oxygen. Then next we are going to balance oxygen by adding H2O as needed. And then last we are going to balance hydrogen by adding H plus ions. And I should point out step 3 is the step where the difference happens if we're operating in a basic solution. And I will point out what the extra step is that we need when we get to the end. So let's apply step 3 to the reaction that we're working on. So the first step, A, is to balance all but hydrogen and oxygen. And so if we look up here, we see we have one iron here and one iron here. So iron is balanced. And here we have one manganese here and one manganese here. So the manganese is balanced. So we don't have to do anything for that. We can move on now to part B and balance the oxygen by adding H2O. So this is 3B, and we're going to work first on the oxidation half reaction, which does not have any imbalance in oxygen, but I'll just write it here so that we can keep track of these together. The reduction reaction did have an imbalance, though, in oxygen. And you see on the left side here we have 4 oxygen atoms, and so we are going to add 4 H2O to the right side. Now step C said to balance the hydrogens, and again for the oxidation half reaction we don't have any hydrogen, so we don't need to do anything with that. But for the reduction reaction we do, so we end up now with MnO4 minus, and we added those 4 water molecules, so now we have 8 hydrogen that we need to add to this side. And then the right side remains unchanged. Okay, so we've now completed step 3. We can move on to step 4. In step 4, we balance each half reaction with respect to charge. By adding electrons as needed. Let's make some room here so that we can work. So let's look at our oxidation half reaction. We had so far Fe2 plus going to Fe3 plus. So we have a charge imbalance here, and we need to add 1 electron to the right side. For our reduction reaction, we had 8 hydrogen ions plus MnO4 minus on the left side, and this was going to Mn2 plus 4 H2O. So we can look here, and on the left side we have 8 plus and 1 minus, so that makes a total of 7 plus. And over here we only have 2 plus, so that means that we need to add 5 electrons to the reduction reaction. Now the next step, step 5, is to make the number of electrons in both half reactions equal so that we can add them together and they will cancel. And we do this just by multiplying through by an integer on one or both reactions as needed. In this case, we have 5 electrons in the reduction reaction and we have 1 electron in the oxidation reaction. So we are going to multiply the oxidation reaction through by 5. So we end up with a 5 here, and a 5 here, and a 5 here. So that's step 5. And then step 6, we add these together and cancel like species as needed. So we add the half reactions. And cancel like species. So when we do this, we end up with the following. On the left-hand side, we have the 8 hydrogen atoms. We have MnO4 minus. And we have those 5 iron ions. And on the right-hand side, we have Mn2 plus aqueous plus 4 H2O and plus the 5 iron atoms. So the final step is simply to check our work, and we want to check for mass and charge balance. And so we can do that with our reaction here. So we'll start with mass, and on the left side we have hydrogen, and we have 8 of those. We have manganese with 1, we have oxygen with 8, and we have iron with 5. On the right hand side we have manganese with 1, hydrogen with 8, oxygen with 4, and iron with 5. And I made a mistake here on the left hand side. Actually, our oxygen is just 4. That comes from right here. That's the only place we have oxygen here. So all of our numbers match up. We are okay on mass balance. Now we can look at charge. On the left hand side, our charge is +8 and -1 and then +10 from the iron here. And so that's a total of 17. So +17 total. And on the right hand side we have +2, and then we have +15 for again +17 total. So that's okay, it balances. So we have now balanced that half reaction. The differences that you'll notice from the original reaction as written are that we now have these hydrogen ions, we have these water molecules, and in this case we have a different stoichiometric coefficient on the iron. The last thing is to talk about how this is different if we have a basic solution. So if we want to balance our redox reaction in a basic solution, and the only difference here is that in step 3, when we are balancing, like before, we balance all atoms except for H and O. Next we balance oxygen by adding H2O. And then we balance hydrogen by adding H+, but if we're doing this in a basic solution we can't have any H+ hanging around, and so this is where the extra step comes in. So if it's a basic solution we need to neutralize the hydrogen atoms, hydrogen ions, by adding OH-, and when we do this we want to add the same number of OH- to both sides of the reaction. And this will keep the balance of hydrogen and oxygen that we have just established the same. So that's the only difference in how to balance a redox reaction for a basic solution.